Hey everyone, this is Dr. Walker. This is video 56C. In this video, we're going to go over a third definition of torque. Torque is defined as the cross product of R and F. So this is our new definition. It turns out that this definition is very similar to the two definitions that we just talked about. Let's look at our picture here. We have a particle at point P right here. Its position vector is described by R, from the origin to that point. There's a force acting on this particle in this direction down here, and the force vector makes an angle phi with the position vector. So if we were to calculate the torque exerted by this force on this particle, we would find a component of F that's perpendicular to the position vector, and that would be F sine phi would multiply by R. As you can see, that's the exact same thing that the cross product is going to give us. A major difference between this definition and the previous ones is that this one does define torque as a vector. Very similar to when we went ahead and defined angular velocity and angular acceleration as vectors. We don't use this definition as often, but it's important to be complete. Do you remember how to take the cross product? Remember the right-hand rule that we learned? You point your fingers in the direction of R, so your fingers should be pointing down this way, and then you fold them in the direction of F. Which way is your thumb pointing? If you're doing this correctly, your thumb will point along the z-axis. So the torque vector points along the axis of rotation. You can see that the position and the force vectors, they lie in the xy plane, and the z-axis is the axis of rotation. So you can take the cross product to get a direction for this torque vector. Let's go ahead and do an example. We have a force F equals 2I plus 3J is applied to a rigid object that is pivoted about a fixed axis aligned along the z-coordinate axis. The force is applied at a point located at R is 4I plus 5J relative to the axis. Find the torque applied to the object. So we can use our cross product definition for torque. Torque is a cross product R cross F. This example just allows us to use a cross product and remember it since we haven't used it in a while. We have 4I plus 5J cross 2I plus 3J. To do this cross product, we can distribute each term. Remember that I cross I is 0 and that J cross J is 0. So when we do 4I cross 2I, we get 0. I'll go ahead and write it down just to be complete. I'll just do 4 times 2. It's going to be I cross I. And then we're going to do 4I plus times 3J cross 3J, so 4 times 3, I cross J. And then we're going to do 5J cross 2I plus 5 times 2. I'm going to write these numbers in parentheses here. And this is going to be J cross I. Oops, this should be a cross, not a dot right here. J cross I. And then the last terms, remember we're using the FOIL method, right? First, outer, inner, and last. So 5 times 3, J cross J. So what we're going to end up with is that I cross I 0, J cross J 0. Do you remember what I cross J is equal to? You can use your right hand rule if you don't remember, but it's equal to K hat. So we're going to have 12K. Then J cross I is negative K. Remember when you switch the order of the unit vectors, you just flip the sign. So minus 10K. Get negative K here. So our final answer for the torque vector is going to be, just write it down here, is going to be 2 k hat. And the unit for torque is newtons times meters. So it's good to be able to use this definition. We'll have other important quantities that are defined in terms of cross product, but we can still use the convention that counterclockwise rotation is positive, clockwise rotation is negative. We're not going to use this property of torque as a vector very often.